Hi, and welcome to Videos.org. This week we're talking to Dr. Clare about her recent work on camouflage and bats. So Dr. Clare, could you quickly give us a summary of the paper?
What we were doing was looking at how bats actually find prey that are sitting motionless on a leaf. So there's bats that echolocate have two different techniques. They can try and capture insects that are moving in the air, so they chase things down, or they can try and get things that are resting on surfaces. And the first behavior is the more common behavior, and the one we know quite a lot about. So it's easier to conceptually think how you can catch something that's moving. So it's easier to see something in motion for a bat using acoustics or echolocation. It's easier for them to find a moving object. The second behavior, taking an object off a surface that's still, is harder because that object isn't moving, and the surface itself can produce background echoes that confuse the acoustic system of bats. So this type of behavior is less well known, and it's less widespread amongst bats. It's a bit more specialized. But there are some real specialist bat species, especially in Central America, that are really good at this. So it's their specialty. And what we were trying to do is work out how it is they actually find a prey on a surface. So some techniques that they might use, some bat species will beat their wings at surfaces to try to make a moth or a beetle move in response, so they get some motion cue. But we wanted to know, how do they do it if there's no motion at all? So we built a system that it's like a little tiny robotic bat in a way. It emits acoustic sound the way a bat would, and it has a receiver, so we can record the echoes that come back. And we took some moths that were dead and we pinned them on surfaces. So some rough rock, some bark, some leaves, and some very smooth slate. And then we recorded the echoes that come back from these surfaces to look at how the bat might perceive a motionless prey. And we had a new technology called tomography that allows us to take lots and lots of echoes and put them together and turn them essentially into a visual representation. So we're now seeing what a bat hears, and allows us to make different kinds of measurements than we could before. We've always been able to look at single echo responses. Now we can look at how many echoes might be integrated into a single image. And so we're seeing what a bat hears, and it gives us access to new signals. And what we found, which was really interesting, is that the prey don't produce very strong signals. So it's still very hard for a bat to see that motionless prey. But what it turns out they might see is actually missing background. So if you were scanning down a really smooth surface like a leaf with our acoustic system, they would sort of see leaf, 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 and then nothing, and then leaf, leaf, leaf. And it's that nothing space that we're calling an acoustic shadow that is the most strong cue in our new way of integrating these echoes. And so what we think might be happening is that the bats have a search image for what their environment should look like. They know what a leaf looks like. And what they're looking for is missing leaf, as opposed to looking for the actual prey, because the prey might be unpredictable. It could be any size, any shape. It could be a moth. It could be a beetle. But these bats hunt in very specific patches, and they will go to the same place every night and scan the same surfaces. So they probably have a really good idea of what their area looks like, their patch. And so they're good at picking up disruptions or aberrations in their hunting environment. And the other thing that we found is that some of the surfaces enhance this effect and some of them conceal it. So if the prey is resting on something that's really rough, like a piece of granite or a piece of bark, it's actually very hard to find them because the shadow is really just part of all the disruptions. So a bark that's very rough produces lots of valleys and troughs and shadows and projections. And the moth or the prey is just another one of those projections. But if they're hunting off a leaf or something that's very smooth, as we call it mirror-like, then that missing background effect is really strong. And this may explain why these specialist hunters really hunt off leaf surfaces only. They don't use other surfaces as much. And so it may be that they're getting much, much stronger signals back when they use ultra-smooth surfaces.
So this missing area, does it also give them an indication to the size of the prey? So they know that it's something they are going to be interested in eating?
We don't know that. Probably, if I sort of speculate on what they're doing, they would probably first notice that there's some missing background. And then they would concentrate on that area. Then they might start picking up the cues from the prey. It's sort of like a first pass. What would you first notice? You might notice that the background's missing. And then if you look really closely, or in their case, you listen really closely, you might start hearing the cues of the prey. So whether they can get much detail on size from this missing background, we don't know. But it might be the first thing they notice in their environment when they're trying to find prey that aren't moving.
So this sort of like almost acoustic camouflage that's going on, has that only been seen in bats' prey, or has it also been found in other animals?
Well, the camouflage component comes from this resting on rough surfaces. So if the insect landed on bark, it might be effectively camouflaged from acoustics because they can't find this shadow effect. We don't know that it's been seen anywhere else. It probably occurs in many species. There's lots of echolocating animals out there. So whales, dolphins, some birds. There's many things that do echolocate. I suspect they can all use this technique. But this is the first time we've actually measured it, partly because the technology, this tomography that allows us to put all these different echoes together into an image, kind of the same way a CT works to take pictures of you in a hospital. It's the same technology, this tomography. This is the first time we've applied it to an ecological or an evolutionary problem to see what a bat is perceiving about its environment. So while I suspect this is the same technique used by lots of animals, it's the first time I know of that we've actually measured it.
So how long did it take you to set up the experiments?
Well, the technology itself took years to develop. It was developed by my colleague Mark Holdreid at the University of Bristol. He's a specialist in acoustics, and he developed this system of turning echoes into visual representations. So the actual setup in that case took a very, very long time. The experiment we did took about a year and a half. It was started by some students, and then we took it on afterwards, and we changed the way we did it. We took new measurements and found better ways of doing it. So we had to refine it a number of times in order to get good measurements out of it. So I would say the whole project for this particular experiment may be about a year and a half, but the technology is several years in the development.
So what's next? Are you going to continue to use this technology and investigate other species, or yes, what's next?
Yes, well, it's not really my primary area of research. My co-author, Mark Holdreid, he's the one who's using it, and he has used it for other experiments. We've both used it for other things. This is the first time we've actually published results from this type of thing, but I think it's ongoing. The next stage of this experiment would be to actually go out into the field, I think, and find out whether the bats are paying attention to these cues. So we have found what we think are new cues. We haven't tested them on live bats. So we could go out and we could use bats in the wild and see if they pay attention to things like missing leaf, to see if they can actually pick up those cues that we think are the strongest ones to them.
That is really interesting. Thank you so much. We're going to put a link to the paper below, and we'll also put a link to your website. Thank you so much for joining us.
Thank you. It was very nice to meet you.
Thank you. Bye.